So this is my lecture 7. So in the last class, we discussed how to design lag lead and lag lead controllers using algebraic method. We followed the method of Enkeshina book. Now we'll consider one example to design lag lead and lag lead controller for a given set of specifications. So we'll just review what are the specifications needed to design lag lead and lag lead controllers, and how we'll proceed for the design first. Then we'll consider the example. So first I'm writing designing. So what are the steps we have to follow for design, that I will say. But before that, I will be saying what are the specification we will be able to meet. So designing lag lead and lag lead controllers. So what are the specification we considered? So all these things we have considered earlier. Specification one is your error constant. Error constant means I should write steady state error constant. Steady state error constant. Steady state error constants. So what are the steady state error constant? As you know, these are, for example, proportional error constant, then velocity error constant, proportional error constant, velocity error constant. Proportional error constant is known as Kp. Similarly, velocity error constant, Kv. Similarly, parabolic constant, all these things are there. So Kp, Kv we will be able to meet. So as you know, what is the steady state error with respect to step reference input? 1 by 1 plus Kp. So similarly, with respect to ramp reference input, what is the steady state error? 1 by Kv. So that means Kp and Kv are the percentage, are the measure of steady state error. Kp is a measure of steady state error with respect to step input. Kv is measure of steady state error with respect to ramp input. So step, ramp, all these inputs are very common in control system design. So these are the steady state error constants we want to meet using lag lead and lag lead control. And then phase margin. So phase margin also we will be trying to, we have to meet. So this is one of the major specification, phase margin. So phase margin is equivalent to zeta damping ratio. Again, damping ratio is proportional to damping ratio. Peak overshoot of a system is depending on damping ratio. So phase margin, damping ratio, peak overshoot, all are correlated. So phase margin is in frequency domain is correlated to damping ratio and peak overshoot in time domain. Similarly, gain cost of frequency. Phase margin I will denote it as this one, and gain crossover frequency also we want to meet. So gain crossover frequency. So gain crossover frequency we will term it as GCF. So gain crossover frequency is also related to speed of the response. So if you want speed of the response more, then gain crossover frequency will be more, and vice versa. So gain crossover frequency in frequency domain is equivalent to, you can say, rise time or settling time in time domain. So all are correlated. These are all frequency domain measures. So these frequency domain measures can be correlated to the time domain measures like that. Now this is the control configuration as we discussed. We will be considering. This is your planned GS, and this is your controller CS. All these things we said earlier when we started lag lead controller design using board plots, 3 classes, 2 classes before last 2 classes. So this is your reference input, this is your output. So for the timing I have not shown any disturbance noise, measurement, all these things. This is a E, this is a tracking error. So CS we termed as CS equal to K into HS. So this is your controller. This is your plant. So this is the cascaded. So that's why lag lead controllers are also known as cascaded control. So this is a cascaded controller design. This is a cascaded controller configuration. Cascaded controller design techniques we have seen using board plots. Now, so CS is a cascaded controller. So CS is cascaded controller. Okay. So as we know that HS, so K is a static gain or servo gain, or you can say servo gain used to meet steady state error constant. All these things I discussed earlier, but before solving a full example, I am again reviewing all these things so that you can understand the things easily. This is K, and then your HS. HS is a normalized part. Normalized lag lead or lag lead controller. Lag lead controller. So normalized means H0 equal to 1. That I discussed. A normalized. So normalized. It is made normalized HS so that the steady state gain static that means steady state error requirement can be met by using KS, and HS will be used. So HS will be used. So this is used to meet the other two specifications, phase margin and GCF specification. So now, well, steady state specification, how will you meet? For example, I have to meet one KP, some KP. What is KP? So meeting steady state specifications. So to meet steady state specifications. How will you meet steady state specifications? So as you know, what is your steady state error? Steady state error ESS. Steady state error with respect to step input ESS equal to 1 by say limit 1 by 1 plus Kp. So this is for 1 by Kp for step input equal to 1 by Kv for ramp input. This is known to you. I think Saurabh derived all these things. So what is your KP? ESS means what? Error. That means limit S. The limit t tends to 0. ESS means steady state error. Tracking error. Tracking error is which one? E. R minus Y. So now what is your KP? KP is where? KP equal to limit S tends to 0. K S tends to 0 into LS. Okay. So what is your LS loop transfer function? S tends to 0 into GS into K into HS. Now you can see limit S tends to 0, HS is equal to 1. So that means limit S tends to 0, K into GS. So since H0 equal to 1, it is a normalized. HS is a normalized transfer function. So similarly, and KV, what is KV? Limit S tends to 0, SLS. Okay. So this is limit S tends to 0, SLS. So this will be again equal to limit S tends to 0 into K into SGS. Because again, since H0 is equal to 1. So HS, because HS is a normalized transfer function, it will not affect the steady state requirement, steady state performance specification. So KP and KV will depend on K and the plant. So in this way, you can meet. Suppose steady state performance, some steady state error, percentage error specification is given. So from that percentage error specification, you can easily find what is your ESS. ESS say 10% means ESS is equal to say 1. Okay, so 0.1. So from there you can easily find what is your KP. And say similarly you can, for a ramp input error due to ramp input, you can also find KB, and then from this relation you can find what will be the K. So this is about steady state error specification. So that means the servo gain or static gain K can meet the steady state error. So now to meet phase margin and GCF. So now this is the critical thing. So we have to design the parameters of the HS, that is normalized first order lag, first order lead, and second order lag lead controller. So first, what you have to do for this. So now when to use given an uncompensated plant. So first this one you should this terminology I will use. Uncompensated plant means here what? So that term I will frequently use. Uncompensated plant means your HS equal to 1. That means normalized lag lead controller is 1. That means there is no controller employed. Means here HS equal to 1. That is called uncompensated system. K will be there. Okay, only if you close the loop with the gain K will be determined based on this. based on that means only if you want to meet error specification. So that means no controller is involved or uncompensated. Uncompensated system means here the terminology may be little bit different. Uncompensated means you may think that it is an open loop system, but it is not open loop. Uncompensated system means here HS equal to 1. Now, note. Okay, I will write that one later. So determine first from given phase margin specification, from given phase margin specification, determine the phase of the compensated system. So compensated means here controller HS is employed. Compensated phase of the compensated system for given determine. So this is the first step. So from the given phase margin specification, determine the phase of the uncompensated system as phase of uncompensated system equal to what is the phase of an if the phase margin is PM, what is the phase of the system? 180 degree, 180 degree plus phase margin as 180 degree plus phase margin. So this is the phase. Given the phase margin, determine the phase of the uncompensated system at phase of the uncompensated at the given GCF as 180 plus PM. So this is your phase of the uncompensated compensated system we want. So now you can find what is the phase of the uncompensated system. So next step is determine the phase of the uncompensated system. At the given GCF. The GCF that I want in the that means the GCF that is given in the specification. So determine the phase of the uncompensated system at given specification. So next is determine the gain in dB of the uncompensated system again at the given GCF. Okay. So now if the phase, so I will write, so this is equal to phi of compensated, this is compensated, and this is phase of the uncompensated system at the given phi UC say uncompensated. Phi C I have not used because phi C I have already used there. So phi com, that's what I have used. So here phi UC I have used, and this is gain of the uncompensated system in dB. Here I am writing as MCU. Okay, so MCU, because MC already I have used. So if so this is your MCU. Well, so now if so this is very crucial step. If phi com is greater than phi UC and MCU, this is what uncompensated. Okay, UC, MCU, don't use MCU. This MUC use uncompensated. MUC. MUC, if phi COM is greater than phi UC and MCOM means phi UC and MUC is negative in dB, then use lead controller. Lead controller using where lead controller with phi C equal to phi com minus phi UC and MC equal to minus UC. So this is very crucial step. So now you see carefully. So when lead controller is needed, when the phase of the uncompensated system suffers from lack of phase margin. So now you see what I have done. I have computed the phase of the compensated system needed at gain cost of frequency, and then I have computed phase of the uncompensated system at gain cost of frequency. Then you will be able to know whether phase lead is needed or not. So if phase lead is needed, if phi com is greater than phi UC, okay, then that much difference you have to provide by the lead controller. Also at gain cost of frequency, what should be the gain? At gain cost of frequency, I want gain should be 0 dB. So now if you see that the uncompensated system at gain cost of frequency is MUC, then how much gain amplification I need? How much gain amplification is need? Minus UMC, so that ultimately UC will be minus that means ultimately that much gain. So MUC will be negative then in that case. So that gain, so minus MUC is what? Minus MUC will be positive because MUC is negative. Okay. So that much gain amplification is needed. So MC equal to minus MUC means MC is here positive. So phi C is positive. MC is positive, then you need so MUC is negative. Here I have said already that phi com greater than this and MUC is negative. That means you have to have some positive some gain amplification, so that at gain cost so that frequency will be the gain cost frequency. That means gain, to make that frequency, if you want omega has to be gain cost frequency, then at that frequency gain should be equal to 1. So that's why here, since at that frequency gain is negative, we have to amplify it. So that's why MC, the amount of amplification, gain amplification required will be minus MC, because it is already in negative. So this is the condition for using lead controller. Similarly, if phi com is less than phi UC and MUC is positive, then positive in dB, then use what? Then use lag controller, where phi C will be equal to, again, phi C, that means phi C is now negative, it will be phi com minus phi UC. Okay, so now phi C will be negative. And MC will be now what? MC will be now negative, so it will be just minus MUC. That means MUC is now positive, so MC will be negative. So in case of lag controller, so if MC is negative and phi C is also negative. So if this is the condition, then lag controller is needed. Now when your lag lead controller is needed, if phi com is greater than phi UC, but the contradictory requirement, but MUC is positive, then use lag lead controller with what? How much gain amplification, how much gain attenuation is needed? Gain attenuation needed will be minus MUC, and how much phase lead is needed? Phi C will be equal to phi com minus phi UC. Clear? So this is the condition. So these are very important steps, all the steps. So I have tried to summarize all the steps so that you can design the controller easily. So this controller design, this lag lead controller design for a given plant is not so easy job. So you have to understand the problem properly. So I have tried to make this here. Okay. Now one just comment you have to write. That is one note. So one note. So I have said that here gain cost of frequency is given. So now in many cases gain cost of frequency has to be chosen by the designer. So in that case, how will you choose the gain cost of frequency? So that is also important. So note, if omega CG or omega C, I will say omega C is not if omega C, is not mentioned, then what will you do? Then omega C you can have some range. You can choose. If you choose omega C is greater than omega of the uncompensated system, that means omega UC is the gain cost frequency of the uncompensated system. If you want gain cost frequency of the compensated system is more than gain cost frequency of the uncompensated system, then the following if you then the following generally holds. The following following must be following should be for then the following are important. Then the following are important. What are those? One. So if WC is greater than, we can use lead controller. WC, if you want greater than this, use WC is greater than WUC. If you want, that means you want to make the system fast. Following are important. Use lead controller. That means you want to make the system fast. If WC is less than omega C is less than omega UC, use lag controller. So well, and for lag lead controller, so use lag controller. The WC, well, this is a very important thing. If omega C is greater than omega UC, use lag controller such that MC is positive and phi C is positive. That also I should write positive. So use lag controller such that MC and phi C are negative. Okay, and then use lag lead. Use lag lead to achieve the intermediate frequency use lag lead for a frequency if MC is negative but phi C is positive. This frequency is normally in between the frequency between cutoff gain cost frequency lag on lead control. Okay, so this is if for a practical system design, omega C will not be mentioned. Even phase also will not be given. You have the designer has to choose which phase will be appropriate. For normally, phase margin should be greater than 30 degree. Similarly, gain cost of frequency will depend how much speed we want. So, a practical system design is a difficult task. A designer has to have a lot of experience. So anyway, these are the general guidelines that will be followed. Now we'll consider one example, and so then you will see how your funda will become much more clear. So one example. So in this example is such that all the controllers will be designed for the single example. Then you will be able to compare its performance and when to choose when to choose what means which controller you will choose under what condition. Although I have summarized all the things above. Anyway, so this is suppose your plant is GS is your 1 over S into S plus 5 into S plus 6. The condition is design design a suitable compensator. So here lag lead or lag lead, it is not said. Suitable controller to meet suitable means lag lead or lag lead wherever required to meet the following specifications. So A is KV equal to 10. That means error. KV means velocity error constant, and B is phase margin equal to 45. So here one thing is choose suitable gain cost frequency omega GCF omega C. So here it is not mentioned what is the GCF. So depending on GCF, as I said, you can choose whether it. So if you choose more omega C more than uncompensated system, then you have to use lead. If it is much less than uncompensated system, then it will lag. If it is in between, then you have to use lag lead. Now we'll be seeing. Now this is solution. We'll be seeing all these things. The solution. So first is to determine servo gain K. This is general. This is a very simple thing. So what is your servo gain? So it is given that what is KV? KV limit S tends to 0, K into S into K into GS here. So that means your KV will be equal to, if you put GS here, K is there. So this will be K by KY. So this is your so here KS. Oh, sorry, this is your 10, not 6. This is your 10. This is your 10. This is not 6. This is 10. So this will be your. This is equal to K by 10. So this implies K will be equal to 10 kV. So this is equal to 10 into. Okay, so I'll write in the next line. This implies your K will be equal to 10 into kV is how much? kV is 10. Well, this kV, this we have to 50. So this will be 500. This will be 500. So that means this part is over. K will remain fixed. Now suppose K you have now fixed. Now what is the gain cost frequency? How will you choose the gain cost frequency if the gain cost frequency is not given? So the way is you have to obtain choosing choice of suitable gain cost frequency. So choice of suitable GCF omega C. So how will you choose? So you have to obtain Bode magnitude data for the uncompensated system. Here, this is a practical kind of design. So normally in exam gain cost of frequency will be given, but still for this system, this system is interesting from practical aspect. So if the gain cost of frequency is not given, then what will you do? So you will obtain the gain phase data for different frequency gain phase data of the uncompensated system. Uncompensated system means K into GS for different frequency. So suppose I am just giving a table of that data. So frequency response data, frequency response data. This is for K into GS. This is your uncompensated loop transfer function. Okay, so this is the table, a tabular format I am trying to give. First is your omega, then phase margin, then MC, then again omega, phase M. So this omega phi, then M in dV means here dV. So here degree, here radian per second. So this is again omega radian per second. So this is degree. So radian per second. This is your again omega radian per second, and this is your M dB. So this is suppose 1.5, 2, 2.5. So this you can easily get from MATLAB. 0.5 and 3.0. So this is minus 107.02. This is minus 115.21 degree. This is minus 123.11 degree, which is minus 130.6. This is minus 136.66. You can easily verify that using MATLAB that you are getting this gain and phase for uncompensated system for these frequencies. This is 19.79 dB. This is 16.01, 13.164. This is 10.81. This is 8.75. And then 4, 6, 8, 9, 10. Up to 10 radian per second data is given. This is minus 150.46. This is minus 171.16. This is minus 186.65 degree. And then this is minus 192.93 degree, and this is minus 198.43 degree, and this is your 5.166.772 minus 5.725, and this is minus 7.935, and this is minus 10. So these are the frequency response data for the uncompensated system, uncompensated gain phase. Now, how will you choose which frequency? So you can easily see. So lead controller first. So for lead controller, how will you choose the frequency range for which lead controller can be designed? So for lead controller, what we saw, first what you have to do for any design, what is the compensated system phase? We need compensated system phase at omega c equal to omega c is not given. Compensated system phase, how much compensated system phase we need? Compensated system phase, this is given, sorry, compensated system phase is compensated system phase if phi COM equal to 180 degree. Compensated system phase equal to how much? So compensated system phase will be minus 180 degree plus phase margin. Okay, so here I think one wrong thing I said. Here it should be minus 180 degree. So here at gain coefficient is not needed, because once phase margin is given, that means your compensated system phase it will be fixed. So yes. So now you see compensated system phase phi com equal to minus 180 plus phase margin. So here phase margin is how much? Phase margin is 45 degrees. So 180 degree plus 45 degree. So that means that means your phi com will be equal to minus 135 degree. So this is the phase of the uncompensated system. So compensated system phase needed. So this is the phase of the compensated system needed. So now you see, for lead controller design, what you have to have? You have to have phi com more than phi uncompensated, right? Phi com more than phi uncompensated, and MUC is negative. So if you see the table, so this is your MUC. This is your MUC. I should write phi. This is phi UC. This is MUC. This is MUC. This is your phi. This is your phi actually. This is your phi. This is your phi UC degree, and this is your MUC. So if you see, so phi com should be for lead controller design, phi com should be greater than phi com should be greater than phi UC, and MUC should be negative. So you see in which range phi com is greater than phi UC. So here phi UC is more negative than phi com. So in this range, that means from 8 to 10 radian per second, 8 to 10, omega equal to 8 to 10, you can see that MUC is negative, and also phi UC is less than phi com. So that's why for lab controller can be designed for this plan in between frequency range 8 to 10. So from the table phi com less than phi com greater than phi UC, and MUC negative for the range 8 less than equal to omega less than equal to 10. So this implies omega c for lead controller design, omega c should be omega c should be chosen for lead controller design. Omega c should be chosen within this range. omega c should be chosen from 8 to 10 radian per second for lead controller design. Okay, so this is your omega 2 equal to 8 to 10 radian per second. So now if you once this frequency selection is over and all this your lead controller is over, so now it will be very simple. All the tools, all the equations we know how to design already you have designed. So let omega equal to omega c equal to say 8 radian per second if I choose. Okay, then what is your phi c? Phi c equal to you can see what is your phi c from this equation. Phi c equal to phi com minus phi uc. So phi com is what? Minus 135 degree minus phi uc is what? Phi uc at 8 radian per second. You can easily see minus 186.65 minus 186.65 degree. So that means equal to this means so this is your 8 radian per second. Now phi c is your this what's called 51.65 degree. So this is your phi c, and then and MC will be how much? And MC will be what? MC is minus of MUC. You see MUC is what? 5.7172 dB. So 5.725 dB. So if you follow the same approach as we have seen earlier for designing lag lead controller using algebraic approach, then so to meet all these specifications, that omega is equal to 8, phi is equal to this is, and the lead controller becomes, I am not designing again, you just check whether you are getting this controller or not. The lead controller becomes to meet all these specifications. Specification means omega c, phi c, and MC. MCDB amplification, MCDB gain amplification, phi c phase lead, and omega c gain cost of frequency. So HS will become 12.725 into S plus 4.78 divided by S plus 60.82. Okay, this please check it. I suggest you. So check it. So now lead controller design. Lead is over lag. Now whether so as I said, given phase margin specification and steady state error specification, you can design lag lead all three controllers. But your omega c will be different. Omega c here I have chosen higher. Now you will see for lag controller design omega c has to be less. So that system will become slow. Same phase margin specification you can get, but here we will see that the gain curve will has to be lowered down. So lag controller design, for lag controller design, what you have to do. So here for lag controller design, so which range you will follow for lag controller design? The same compensation phi com will same. So now you have to see where phi com is less. For lag controller design, you have to see where MUC is positive. So MUC positive starts from so MUC is positive up to 6 radian per second. But you also have to see where phi UC, where phi MUC for lag controller design. If you see MUC is positive and phi com is less than phi UC. So phi UC is more. Where phi UC is more than 135 degree minus 135 degree. So you can see phi UC is more, as well as MUC is positive in dB from 1 to 2.5 degree. So 2.5 radian per second. So then you can design the controller. So here you can see that from the frequency response data. So you write from frequency response data phi UC is more than phi UC is more than phi UC is more than phi what phi UC is more than your phi compensated. So this is your phi com. Phi UC is more than phi com and MUC positive for omega for 1 less than equal to omega less than equal to 1 less than equal to omega less than equal to 2.5. Thus here 1 less so omega should lie omega should lie in between 1 to 2.5 radian per second. Okay. So now one thing you can so in case of phase lag controller, main objective is to provide attenuation. So you should have as less phase lag as possible. Main objective is gain attenuation. So phase lag it should provide much less. So phase lag is actually not allowed much in practice. Phase lag, if it is more, it will be much lower. So that's why maximum frequency which are available, which you can have, that you can design. So here maximum frequency for which lag controller can be designed is 2.5. So we choose say in between, that is 2 radian per second, 2 radian per second say. So let us choose, let omega c equal to 2 radian per second. If you take less than 2 radian per second, then it will be slow. 1 radian plus 1 radian or 1.5 radian. So 2.5 radian you can also design. 2.5 radian is a fast lag controller. Possible you can design for this system. Omega c equal to 2 radian per second. So now here, so omega c is 2 radian per second. What is your phi c? Then phi c equal to 135. Your phi c will be what? Phi c will be from this specification. From this, phi c will be phi com minus phi uc. So phi com is no. Here in case of lag controller what? Phi com minus phi uc. Phi com is how much? Yeah, phi com minus phi uc. So phi c will be phi com minus phi uc. So this will be minus this will be phi c will be minus 11.89 degrees. So this means phase lag. And MC will be equal to minus MUC. So that means equal to minus if you see the frequency response data, from frequency response data, what is the gain? This is minus, this is MUC is 13.164. So this will be minus 13.164 dB. So these are the data we these are the data we need for lag controller design. Omega C is 2 radian per second, phi C is this, M C is this. So then the controller you can easily design, which you have already discussed. Then the lag controller becomes HS equal to, you can easily verify, 2124 into S plus 0.543 divided by S plus 0.1153. Okay, so I'm just writing, check it. Okay. Better to check it. I have checked it, but you must check. So now lag lead controller design. So for lag lead controller, how will you design and what is the frequency we will choose? So for lag lead controller design, what is the condition? Lag lead controller design, and the phase lead we want to provide and gain attenuation. That means we have to see the frequency range where phi UC, where MUC is negative, but your phi UC is what? Phi UC is less than phi compensated. So that means from the frequency response data, you can see that MUC is positive, but phi UC is less than phi com from 3 radian per second to 6 radian per second. From 3 to 6, from 3 to 6 radian per second. From 3 to 6 radian per second, this is happening. So from 3 to 6 radian per second, you can design phase lag lead controller. So here, so I'm not again elaborating. Here omega C is here. Omega C is 3 to, omega C should be 3 to what I said, 3 to 6 radian, right? 3 to 6. Omega C 3 to 6 radian per second. Why? Since in this range, MUC is positive, but phi UC is less than phi com. Phi UC, you can see phi UC is less than phi com. Yeah, phi UC has to be less than phi com. Yes. So we'll take some frequency, say in this range, omega is equal to 4 radian per second. So we'll take this one. Then phi C, how much phi C we need? Phi C will be, phi C you can easily see, phase lead will be minus 135 degree, minus how much at omega C equal to 4 radian per second. What is the frequency? What is the phase? Minus 150.46. Minus 150.46. So this is minus 150.46. degree. So this will imply phi c equal to 15.46 degree. So 15.46 degree, and MC, how much MC we need? MC equal to minus m of UC. So that means equal to, you can easily see from the data, 5.166 dB. From the data, just you see at 4. So this is MUC. So minus MUC means 5.166 dB. So these are the this much gain attenuation we need, this much phase lead we need, and this is the frequency, gain cost of frequency we want. Frequency. So then the lead controller becomes, lead controller you can easily design following the same procedure as already discussed using algebraic approach. So then, with phi 2 we have to take now phase lag, small phase lag that will be provided by the lag part at this frequency. Say we are assuming, say 2 degree, with phi c equal to 2 degree, one obtains the lag lead controller, say HS equal to S plus 5.36236 into S plus 0.26331 divided by S plus 11.44735 into S plus 0.1233. Okay, so this is your lead controller. So this again please check it. So now we want to see the board plot and time response of these three design, and we want to see what is the difference in the Bode plot characteristics and time response characteristics. So I have simulated all these three. I have simulated this plant with all these three controllers and the board plot and step responses. I have got, just I will attach here. Just I will try to attach tools option page, and this is tools image. So it is in download. So it is in downloads. Where is the download index? It is in download file. Desktop C drive. So okay, in C drive download folder, it is not there. Okay, I can download desktop and then download folder I cannot access from here. Plus no, it is not coming. Just one use. just wait. Colleagues. Master figure because must put files from here from a download. Just wait and download. I'll go to my computer and then downloads. I'll bring these two files. Copy and then I'll paste to desktop and desktop. Paste. The another file is there. Copy. I'll desktop. I'll save there in desktop. Same thing I copied. Copy. Paste. So now I think I will be able to attach. So tools, image. Yeah, so now desktop. Yeah, first board plot I want to attach. Open. So I'll just expand it a little bit so that it is visible well. Yeah. Okay. So this is the board plot. So this I'll write here. Board plot that we have got, and the board plot, from the board plot you can see that this is the uncompensated system, and this is your lead controller, this is your lag controller, and in between is the lag lead controller. So you can see that the gain cost of frequency in case of a lead controller has increased compared to the uncompensated system, and lag controller has gain cost of frequency reduced. So in case of lead control, lag controller, the gain cost of frequency is 2 radian per second, and in case of lag controller, the gain cost of frequency is your how much for how much you have designed this is 8 radian per second, and the uncompensated system has gain cost of frequency approximately 6 radian per second. Okay. And then you can also see in case of lead controller, the phase, because phase lead has occurred, so the phase curve has shifted up. And in case of lag controller, phase curve has shifted down. And in case of lag controller, also gain curve has shifted down so as to reduce the gain cost of frequency. So these are the things happening in case of lag lead and lag lead controller. So and in case of lag lead controller, all the things are getting traded off. So if you see these things in what is the point? Point is point is with lead controller, dB curve gets shifted up, dB as well and phase curves, get shifted up, and with lag controller, what happened? dB and phase, dB as well as phase, dB and phase, dB as well as phase, right? dB and phase get shifted down. And in case of lag lead controller, a compromisation is made. A compromisation is made. A compromisation is made. Okay. So now if you see the frequency response, time response. So time response also will attach options, tools, image, time response with step response. So I have simulated this one. So okay, so this is the time response. With 3 controllers, and you can see, as expected, the uncompensated system. That means if you do not use any controller, that means HS equal to 1. Only gain is the controller. Then you can see the response is ringing, and with lead controller you can see the response is very fast, and with lag controller the response is sluggish, little bit much, well, sluggish, it is sluggish, and with lag lead controller the responses are responses traded off well. So the observation is with lead controller. Now uncompensated response is oscillatory. With the lead compare system is fast. With lag compensator the system becomes slow, and with lag lead controller response is traded off. That means in between lag, response characteristics like in between lag and lead, not too fast, not too slow. So this is the this is the example I have completed, and in the same example we have designed all 3 controllers, lag lead and lag lead controller. I have given a summary of the design approach, and if the gain cursor frequency is not given, how to choose the gain cursor frequency depending on the controller you want to employ, that is also given. Just I will see overall if there is any error. minor error, major error will not be there, but minor, just for example, this would be minus 180 degree. This kind of minor error may be there. So if I find later on also, I will let you know. If you find when you will go through it, then also please let me know. Phase of the uncompensated systems. This one, if I is then you see. Percent 10. 8 to 10 radian per second. Okay. Well, I think everything is fine now. Okay. Thank you.